Okay, so antiderivatives, since we're getting down to the wire, this is the last week before spring break. Yay! Okay, and after spring break, we come back, we've got a couple more weeks of, a little bit of units, and then test prep, all test prep. So that's what that last couple is, just test prep. Anyway, so let's go through here. Definition of an antiderivative. A function, capital F, is called an antiderivative of the function of lowercase script f if f, capital F, prime of x is equal to f of x times capital F prime of x is equal to f of x for all x in the domain of f. Now, does anyone understand what the hell that means?
No.
Probably not. So, right here, g and f are differential functions. F prime is equal to g prime. For all numbers in x in the interval, then exists a number for c in which that f of x is equal to g of x plus c at a point. That plus c is going to be what gets most people here. So when we take an antiderivative and we're actually trying to find the initial, whatever initial value it is, because if I take a derivative of the number 5, what is the derivative of number 5? 0. But if I take an antiderivative and I want to try and get back to that, 0 is not going to give me some value, some constant that is there. So that's where we get our plus c from, because there is going to be some constant that ended up becoming 0 that is no longer part of my equation. There we go. If a function, capital F, is an antiderivative of f and defined on an interval I, any other antiderivative of f has form, capital F, of x plus c, where c is the arbitrary constant. That's that c I was telling you about. Then when I took the derivative of the number 5, it became 0. But when I go antiderivative, I don't have any evidence that says what that constant was supposed to be. So, antiderivative of this. Okay, so right there, the first one. If it's of 0, I have to add something, right? Okay, if my derivative, like I said, of 5 became 0, but now I have to go from 0 back up to 5. I can't really do that. So I know that there is some constant. So this is going to turn into some constant, that there was some constant there. Because I said that if I started with 5, I got the derivative to 0, but I can't go from 0 back up to 5. I know that there is some constant there. That's what that c represents. Make sense? Okay, good. All right, so g of theta, okay, negative sine theta. So I'm going to do my circle of derivatives. We start off with sine here, cosine here, negative sine here, negative cosine here. And this is my derivatives, right? And the derivatives go this way, don't they? Yes? So what do you think an antiderivative should do? Go the other way, right? So I had a foreign kid in my class when I was doing this, and so if this is clockwise, going backwards is anti-clockwise. The foreign kid was like, it's anti-clockwise. What? Yeah, I was struggling with that one. I'm like, oh, okay. So he's not wrong. It's anti-clockwise, so it's against clockwise. So we refer to it as counterclockwise. So when the foreign kid heard that word, he's like, I've never heard that word before in my life. I'm like, okay. So we are going in this direction for my antiderivatives. So negative sine is going to give me positive cosine, right? So this is going to be capital G of theta is equal to positive cosine of theta plus c. Yes, I do. Do you know why I always do that? Because there could have been some constant there. Not saying that the constant, could the constant be 0? It could be 0, so it's not implying that there must have been, but there is a possibility of it being a constant there. Because quite often I would just give you, say, hey, find the derivative of cosine, and you would tell me, hey, it's going to be negative sign, right? But sometimes you would see a problem that would say, find the derivative of cosine plus 1, would still give you the same answer, right? Yeah? And so we need to account for the fact that there could have been something there. This next one here, antiderivative. So new page right here, h of x is x to 1/2. Now, if I were to take a derivative, okay, I'm going to take a derivative and I'm going to show you the steps here, step by step. So my derivative, so x squared, the derivative of that is going to do what? Bring this out front and multiply, right? And multiply, right? So that would go out there, and then it turns into 2x, and then it's 2 minus 1 right there, right? I subtract. So order of operation is backwards. So right here, if I'm multiplying out front, how do I undo a multiplication? I would divide. How do I undo subtracting 1? Add 1. There we go. So I'm going to add 1, and then, okay, so this right here is going to give me 2x to the first, right? Say yes. Okay, 2x to the first. So now I'm going to take the antiderivative of that. So antiderivative. So I'm going to start by adding 1, and then 1 plus 1 is divided by 2, right there. So when I do that to get my antiderivative, that's going to give me, stop it! That's going to give me 2x squared over 2. And are we back to my just x squared? Yes. So the steps going backwards. Steps going backwards. So write down these steps. So what do I do first? Add 1 to my exponent. Did you write that down? Did you carve it in your arm like some emo kid?
Yes.
Yeah, that's what I figured. Okay. Add 1 to the exponent and then divide by that exponent.
By the new
Yeah, the new exponent. That's what we're doing. So let's go back to my h of x right here. So add 1 to the exponent. So if I'm adding 1, I'm adding how much? I gotta add 1, right?
Yeah.
So how would I add that? So I'd say plus what? 2 over 2, right? 2 halves? Okay, so that would be, so let's see, that's going to give me x to the 3 halves, right? And then I have to do what? Divide by? But wait, there's more. I have a fraction over fraction, right? I have a fraction with a fraction in the bottom. So if I'm dividing by fraction, what can I do instead? By the reciprocal. Multiply by the reciprocal. Instead of dividing by 3 halves, I'm going to multiply by 2/3. So 2/3 x to the 3 halves. That's a 3 halves. Yeah. So did I just blow your mind, Christian?
That's
Kind of.
literally the same.
When you have a fraction or a fraction, like when you had the 2/3, the 3/2 on the bottom, you have just multiplied by the denominator on the bottom, on the top.
Mm-hmm. Yeah.
Okay, I'll just make sure that was correct. 'Cause that's
Yeah.
what you told me. Okay, I just want to make sure that was still correct.
Mm-hmm. All right. So not so bad, right? Okay. This is why I say fractions are your friends, not food. Here is a whole bunch of tables to go along with it. So if I were to ask, be like, hey, what's the derivative of secant? What's the derivative of secant? Isn't it secant tangent? So we can look at this and go backwards and get derivatives, or forward to get my antiderivatives. Now, some of these are kind of important, like these ln ones, okay? These are important to remember. Another one is the arcs right here. These arcs here are important. We did some of these already. And hyperbolic, that's what those H is. So I hate those. Yeah. It's on your notes. It's on that slide.
But they're blurry.
Huh?
It's blurry.
Oh, it's blurry? Because you're not wearing your glasses. It's right here.
No, they're blurry.
You're not wearing your glasses either. Okay,
No, I
where it
haven't.
says sine h of x, those are hyperbolic.
You know I wear glasses.
Hmm?
You know I wear glasses.
Mm-hmm.
How?
Yeah, you had them.
I did.
You
Yeah.
were-
So, anyway. Sums and rules. So it's the same as adding and subtracting, the same thing. Okay. An antiderivative of the sum of functions equal to the sum of the antiderivative of the functions. An antiderivative of a number times a function equals the number times a antiderivative of the function. Doesn't that make sense? Perfect sense. If k is a real number and f is an antiderivative of f, then k times f is an antiderivative of k of lowercase script f. So it's basically you're factoring out a constant k times your derivative. So can I factor out a number and then take my derivative and then multiply it back out? I figured that, okay. Yeah, a lot of people get to calculus and they don't know what factoring is. Sarcasm. Find all the antiderivatives of this. Okay. This one should be easy. You ready? This is gonna give me capital F of x equals e to the x. Remember, what do I do first?
You
Add 1 to the exponent, right?
Yeah.
So it's gonna be x third, and then divide by 3. There you go.
And you just leave the 6 alone?
Leave the 6 alone for right now. Because that's where all the magic happens with your exponent and your variable, right? That's where the magic happens right there. So add 1 to the exponent and then divide by that. Alright, it says negative sine x. Positive, okay, so positive cosine x
Plus cheese.
plus c. Right there, that c is going to be the same constant. So if I took each three of these individually, if I consider them all three individuals, each one would have its own c, wouldn't it? Okay, and then as I combine those together, if they all had their own c, it'd be c1, c2, c3. But they're all just some constant, aren't they? So it's still just whatever constant that comes out to be. So I only need one constant for all those. Okay? So a constant plus a constant is a constant. There we go. And so if I add another constant to that, it is a constant. So therefore, I only need a, there we go. So the only thing I can do is actually clean this up. There we go, that's it. Oh, happy day. Yeah, I got enough time. Okay, equation in the form of dy dx is equal to f of x is an example of differential equation. So, this is where I said, you know, the Leibniz notation, right, comes into play. Any function y equals capital F of x, or which dy dx is equal to f of x is a solution of the differential equation. The general solution of a differential equation consists of all the antiderivatives of f. So that means it's always going to have my plus c, right? Plus, you suck, stop it. Right there. Okay, that's what that means. The boundary condition, initial condition, this is going to be your key word for all these problems in here. Initial condition used in the conjunction with the general solution to find the particular solution. So, a particular solution says solve for C. That's what all that means. If you have an initial condition, stop it! You have an initial condition, and it says a particular solution, that means solve for C. You're going to get some values to help you solve for C. Here it is right here. Solve the differential equation with the boundary condition when x equals 3, then y is negative 1. Usually, they will give you just this. And they'll give you just that, and then you have to find some, and you'll have to work your way through this. But right here you have both. You have the x and the y, so that's going to help you out. So verify the solution. Okay. So I am going to separate this is important because once we actually get to integrals, that's where this comes into play here. Okay, that parentheses is important, okay? So, break it up. I get dy is equal to x squared plus 2x plus 1 dx. And so I am going to take the antiderivative of this for y. So I get, this one's going to turn into just y equals, remember, add 1, and then divide. So that's going to be x cubed over 3 plus 2x squared over 2 plus 1x, right? Because that's a number 1. Okay, it would be x to the 0, but I'm going to add 1, right? So a constant is going to get a variable. Okay, so I get that, and then that takes care of that for my dx's. But I have my plus c. Because there is or was some constant in between there. Clean this piece up. And now I have an initial condition. So initial condition means I have an x and I have a y here. So I'm going to replace my x and y. Y is -1 equals x is 3. So this is 3 cubed over 3 plus 3 squared plus 3 plus c. My math, 3 to the 3rd power is 27. 27 divided by 3, oh, stop it. So this is going to give me 27 divided by 3 is 9 plus 9 plus 3. My board hates me today. So that's going to be 21, 18, 21. Right here is positive, right? Positive 21, and I got to move it to the other side. So I'm going to subtract 21, so that's going to make C -22.
Why would 3 cubed over 3 turn to 9?
What's 3 to the 3rd power?
9.
Nope,
Oh.
that's 3 times 3. So 3 times 3 is
Oh.
9, times 3 again is 27. That's why I get 27 there. So 27 divided by 3 is 9.
Yeah.
Yes? Okay, so before my board freaks out again, so I said C is -22. And let's put that into my equation. So I'm going to say that y is equal to x cubed over 3 plus x squared plus x minus 22, right? So this is my particular solution. That's a particular solution. That's going to be the solution for that whole thing, because it gives me the point in which that's going to help me out with the constant. Okay, so right here, we're going to go back and do it. We're going to go back and do the derivative of this. Let's take the derivative, because I'm going to verify this now. So this is going to be dy dx is equal to the derivative multiplied by 3, right? So it's 3x squared over 3 plus 2x squared plus 1. That goes away, right? Huh? Oh, thank you. Sorry. I keep staring as my numbers keep disappearing here. There you go. Alright, and then, bam, I get dy dx equals x squared plus 2x plus 1. Wasn't this my original? Come on, stop. F it with me, board. You guys get the gist of it, right?
Yeah. Wait, so we had the thing here, and then we found the particular. Why is it taking the derivative of it going back to the original function?
The question said what? uses the F word and it's not gonna be factored. Verify
Oh.
verify the solution. Yes?
I get it. Jesus, Nephi.
No, it's when he drew the box around it and immediately.
I mean, I get how to get there, but I don't understand
Why did we go back to it?
Yeah, like how, like, you know?
We took our answer
Yeah.
and took the derivative of our answer. Because everything that we're working towards is a antiderivative, right?
Mm-hmm.
And by taking the derivative of my answer, verified my initial problem.
And the initials that okay.
Right here.
He gave us the derivative.
They gave us the derivative and then we got the antiderivative?
Antiderivative.
And then we went back and that's why we got the derivative again?
Yes, and then we went back to verify it, that by taking the derivative of my answer, that's exactly what I was supposed to have.
Okay, that makes sense.
Alright, all people, like, share, subscribe. And so if you wanna listen to Nephi laugh out loud, I don't think I've ever heard him laugh out loud at anything before, but yeah.
It's that box. Those boxes were a great point.